Okay, so chapter 6 deals with the area of thermochemistry. And basically, in this chapter, we'll be looking at the relationship between chemical reactions and the energy changes that are associated with such reactions. So the first thing we need to talk about is, what do we mean by this term energy? And the definition of energy is the capacity to do work. So that begs the question, what does work mean, right? And work basically is said to be done when force is applied to an object and the object moves, all right? So if I'm pushing on this cup, for example, and it moves, then I'm doing work on the cup, and therefore I'm expending energy in order to move the cup, all right? So that's basically what energy is all about. So the term energy, I think the original word was in Latin, means literally work within. However, an object does not contain work, all right? And there are two main types of energy. You have what is known as potential energy, which is the energy an object has by virtue of its position or composition, and kinetic energy, which is the energy an object have by virtue of its motion, all right? And there's a formula that we can use to calculate the kinetic energy. It's given right here. Kinetic energy is equal to half times m times v squared. M is the mass of the object in kilograms, and v is the speed or velocity of the object in meters per second, right? So as a consequence of that, if the mass is in kilograms and the speed is in meters per second, which is squared, that means that the unit of energy can be expressed as kilograms, meters per second, and all of that squared. And there is a name given to that unit, collection of unit, is called the joule unit. So the joule unit is the same thing as kilograms, meters squared over second squared, all right? So that's the metric unit of energy. There's another unit of energy which is not metric, known as the calorie, which I think we'll talk about later on. But before we get to that, let's talk about some basic terms that you need to be aware of. As I said before, thermochemistry is basically the study of energy change that occurs in a chemical reaction. And when it comes to examining these things, it's important that you're able to identify what is known as a system, which is a part of the universe that is being studied, and the surroundings, which would be the rest of the universe, right? So the system can be, anything really that you're focusing on in terms of examining the changes, like a test tube, a beaker, whatever, all right? While the surroundings would be the rest of the system. Okay, so let's talk about the different types of systems. You have what is known as the open system, where energy and matter can be exchanged between the system and the surroundings. Then you have closed systems, where energy can be exchanged, but matter cannot be exchanged between the system and surroundings. And then finally, you have what is known as an isolated system, where there is no exchange of matter or energy between the system and the surroundings, right? So these are the three types of systems that we'll be concerned with, all right? So in this particular case here, where you have energy exchange between the system and surroundings, but no exchange of matter, then this would be an example of a closed system, all right? But in the case of an isolated system, neither matter or energy will be exchanged between the system and the surroundings, all right? So this is an example of a closed system, all right? And as I said before, this would be an example of, hold on, oh, okay. So this is a closed system, as I said before. I was just looking at this question in the box. It said, after the lid of the jar is unscrewed, what kind of system is it? Well, the answer would be, it would be an open system, because now you can have the exchange of matter and energy between the system and the surroundings. Okay. As far as energy is concerned, there are two main types when it comes to chemical reactions and molecular systems. You have what is known as the internal energy, symbolized oftentimes by the letter U. In some textbooks, they use the letter E to symbolize it, and that is the total energy contained within a system. Part of the energy that is internal is kinetic, as I said before. The kinetic energy is the energy an object has by virtue of its motion. So the kinetic energy could be in the form of, as a result of, I should say, translational motion, rotational motion, vibrational motion. These are all collectively different forms of kinetic energy, right? And collectively, these are sometimes called thermal energy. And the reason why is because the thermal energy is a reflection of the temperature, which is directly related to the different forms of kinetic energy. And we saw this earlier in chapter 5 when it comes to if you remember, there was a formula I showed you where the kinetic energy is equal to some constant multiplied by temperature in Kelvin, right? So there's a direct relationship between the temperature in Kelvin and the kinetic energy, all right? So that's why it's called thermal energy sometimes. Oops. Okay, what did I do wrong? Okay, and then the other part of the internal energy is potential. And this is where we're talking about the type of intramolecular force of attraction as a result of the locations of atoms and bonds, right? And sometimes these are called chemical energy because usually whenever you have a change in energy of a chemical reaction, usually that involves, well, not usually, always involves the breaking and formation of bonds, all right? So the energy changes that would occur as a result of that, we call that chemical energy. All right, then we have this term heat, all right, which is another term that you have to be familiar with. Here's a definition of what heat means. Heat is the energy transfer between a system and its surroundings caused by a temperature difference, right? So an example is given here, a hypothetical example. So let's say you have a hypothetical thin wall here. On one side of it, you have argon, gas molecules or gas atoms, and the other side you have nitrogen molecules. And let's say that the argon molecules, or argon atoms, I should say, are more energetic, and they hit this wall here, then what will happen is that you're going to have the energy transfer from over here to the molecules on this side, and that will be in the form of heat, right? So basically heat energy will be transferred from the more energetic molecules or atoms to the less energetic molecules. And that heat transfer will continue until both sides will have the same temperature. We call that a state of thermal equilibrium, right? Thermal equilibrium is where you have the temperature on both sides of this particular situation being the same. And therefore, when that happens, there's no more heat transfer, all right? And that is true. I mean, if you think about it, you know, and we're going to see some examples of this. You know, if you put something like a hot metal in contact with a cooler metal, then basically the heat transfer will go from the hotter object to the cooler object. And therefore, as a result, you're going to achieve thermal equilibrium eventually. And then the heat transfer will stop. Now, this is asking a question. How do the root mean squared speeds of argon atoms and nitrogen molecules compare at the point of equilibrium? Well, one way of looking at this or tackling this question is we look at the formula that I showed you earlier for the kinetic energy. What am I going to do this? Okay, kinetic energy of helium is equal to half the mass of the helium atom times the velocity of the helium atom squared. And a similar formula would be for the kinetic energy of the nitrogen molecule would be equal to half the mass of the molecule, nitrogen, times the velocity of the nitrogen molecule squared. So at thermal equilibrium, these two terms will be equal to each other, right? Which means that these two expressions will be equal to each other, right? So therefore, we can say that since these two are equal to each other, we can cancel out the half here and here. So you're going to end up with MHE VHE squared is equal to MN2 is equal to, not equal to, times VN2 squared. So the question is asking, how do the root mean squared speeds of the argon atom? Oh, what did I say here? It should be argon. Let me replace helium with argon here, 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 here. Okay, so this would be argon here, and argon here, and this would be argon here, and argon here. Okay, so we're comparing the root mean squared speed of argon to that of nitrogen. All right. So basically, after dividing both sides by VN2 squared and dividing both sides by MAR, so this will cancel out with that. MAR, that will cancel out with that. I'm going to end up with VAR over VN2 is equal to the square root of MN2 over MAR. And all we have to do from here is to look up the molar masses of nitrogen, which in the case of N2, that will be 28.02. In the case of argon, 39.95. And then we find the square root of that. Divide 28.02, divide that by 39.95, and then find the square root of that. And according to my calculation, this works out to be equal to 0.8375, right? So basically, the velocity of the argon atoms will be equal to 0.8375 times the velocity of the nitrogen molecule. So that is basically the answer to the question being asked here. All right. Okay. So that's as far as heat is concerned. And then the other term that we need to be concerned with is work. As I said before, work is said to be done when force is applied to an object and the object moves, right? And one thing that work has in common with heat is that basically you're transferring energy to the object. So basically before you apply force to the object and then you do so, apply the force and then it moves, the difference in energy between before you apply the force and afterwards, that would be equal to the work done on that object, all right? Unlike heat, work is caused by force, moving through a distance, right? Whereas heat is caused by a temperature difference. And if you have a negative quantity of work, it signifies that the system is losing heat. And what that means basically is that the system is doing work on the surroundings. On the other hand, if the work is positive, that means that the system is gaining energy, which means that work is done on the system, all right? And what you're going to see a lot in this particular chapter is the importance of interpreting the sign of the energy changes that will occur, all right? Very important, all right? So it says here, there is no such thing as negative energy or positive energy. The sign of work or heat basically signifies the direction of energy flow, all right? So if an object is gaining energy, right, then the sign associated with that change will be positive. If an object is losing energy, then the sign associated with that change will be negative. So all that you're going to see come into play when it comes to solving problems. Now, here is another hypothetical situation where we have a gas trapped in this container, and this is purely hypothetical. So this plate right here, we're going to assume that the plate is free moving and there's no friction between the plate and the vessel, all right? And we have a gas trap here, right? So the initial volume of the gas is V initial right here, right? And if the gas expands, it expands to V final right here. So there's going to be a change in volume here. And we can actually calculate the work that is done on the gas based on that change. And it is given by this equation here. W, which is the work done on the gas, is equal to minus P delta V. Delta V, I'm not sure if you're familiar with the symbol of delta in math. It means change, right? So delta V means change in V, all right? So this is a formula that we can use to calculate the work that is done on the gas, all right? And they call this pressure volume work for obvious reasons, because of the pressure term and the volume term that is in this equation, all right? Now at this juncture, I want to introduce now something that I'm quite sure you have not met before, this whole concept of state function, right? So I'm quite sure by now, based on your previous experience, you have heard of the term state referring to the different phases of matter, solid, liquid, and gas, right? Well, to be perfectly frank, in chemistry and in physics and other related fields, the term state is a much broader term than just solid, liquid, or gas, right? The state of a system is its exact condition at a fixed instant, right? And the state is determined by, among other things, the kind and amount of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature of the system, all right? Now, so just to give an example, if I were to, let's say I have a piece of iron, which is a solid, and let's say that I had it at 25 degrees Celsius, right? And then let's say I heat it to get the same metal, iron, which is a solid, but this time it is at 75 degrees Celsius, right? Believe it or not, this represents a change in state, simply because the temperature has changed, right? So even though it's within the same solid phase, right? But because the temperature has changed, the state has changed, right? Or if I have, let's say, hydrogen gas, and let's say it was at 1 atmosphere here, and let's say that I change the pressure from 1 atmosphere to 4 atmospheres. Again, this is another change in state because the pressure has changed, right? So that's something you need to keep in mind when it comes to understanding in this particular chapter what we mean by state, right? As stated here, the state is determined by not only temperature, not only pressure, and not only whether or not it's a solid, liquid, or gas, but it is determined by the amounts and kinds of matter present and the structure of this matter at the molecular level. So you might have the same element existing, for example, in two different forms in terms of how the atoms are structured. If you go from one to the other, that will be another change in state. Now, a state function is a quantitative property that has a value that depends only on the present state of the system and does not depend on how the state has been reached, right? So in other words, it does not depend on the history of the system, all right? And this now leads us to the first law of thermodynamics, also known as the law of conservation of energy. And this is something you may have met before. It says in a physical or chemical change, energy can be exchanged between the system and surroundings, but no energy can be created or destroyed. So another way of stating this is that the energy is conserved whenever a substance or if there's a change occurring within a substance, right? And that change could be chemical or it could be a physical change, right? Now, or even more succinctly, it can be expressed this way. Energy cannot be created or destroyed. And the inference that you can derive from that statement is that the internal energy chain of a system is simply the difference between the initial and final states, right? So basically the change in internal energy would be equal to the final internal energy value minus the initial internal energy value, all right? Now, the thing about this equation is that you cannot, nobody has been able to, and nobody can determine what these values are, right? We do know that the change in internal energy is equal to the difference between the final internal energy and the initial, but to determine these is virtually impossible, right? So basically, we can measure this in terms of the energy change that occurs as heat and or work. And there's an equation which relates this internal energy change to the heat change, which is represented by the letter Q, and the work that is done on the system, which is represented by W. And that is this equation right here. The internal energy is equal to Q, which is the amount of heat change occurring, plus W, which is the work that is done on the system. All right, so that's the internal energy. Now, as I said before, the sign convention is very important. And I think I made mention of this earlier, but I'm going to say it again. When energy is entering the system, the energy change will be positive, right? And that can be done by either heat absorbed by the system or work done on the system. All right. Now, if energy is leaving the system, then that energy change will be negative, and that can be done by either heat given off by the system or work done by the system. All right. So very important that you understand the meaning of the signs associated with the energy changes occurring in each case. All right. So just to illustrate the importance of the sign when you do these types of calculations, here's an example. It says a gas does 135 joules of work while expanding, and at the same time, it absorbs 156 joules of heat. What is the change in internal energy? Now remember, the change in internal energy is equal to Q plus W. All right. So, according to the question, the gas does 135 joules of heat. So when it says does, what does that mean? It means that W is negative. So W will be equal to minus 135 joules of heat, right? Because the system is doing the work and therefore will lose that amount of energy. And then it says at the same time, it absorbs 156 joules of heat, which means that Q, the heat, would be positive 156 joules. So that's what you have to keep in mind when you're doing this problem. So therefore, the answer here would be 156 joules plus minus 135 joules, which is the heat change or the energy change due to work done by the system. So that would be 156 minus 135. So according to my calculation, this works out to be equal to 21 joules. And that's how that is done. All right. So when it comes to these problems, it's very important that you understand and interpret what the signs would be based on the information provided. All right. Okay. Any questions so far? Any questions? Any questions? Okay, so let's talk about heats of reaction. So, as I said before at the beginning, in this chapter, we'll be concerned with the energy changes associated with chemical reactions. So, that's what we're going to discuss here. So, basically, the heat of reaction, Q reaction, is the amount of heat exchanged between the system and its surroundings, right? So, in this regards, you have two types of reactions. Excuse me. You have what are known as exothermic reactions. Exothermic reactions are reactions where it gives off heat, right? So an example of this would be if I were to take a test tube and if I were to add, let's say, sodium hydroxide to it, and I make sure it dissolves. If you feel the outside of the test tube, it's going to feel warm, right? Or even hot, depending on how much of the sodium hydroxide you have added to it. And the reason why that happens is because the dissolution of sodium hydroxide is an exothermic process. It generates heat, and therefore when you feel the outside of the test tube, it's going to feel hot or warm, right? So as stated here, if you're dealing with an isolated system, then when you have an exothermic reaction taking place, because heat is given off, the temperature will increase, right? And therefore, as a result, the system will go from a higher to a lower energy level, and therefore the Q of reaction will be negative. All right. So in an exothermic reaction, heat is given off. As you go from reactants to products, there is a loss of energy. The products will have a lower amount of energy compared to the reactants, and therefore Q reaction will be negative. On the other hand, an endothermic reaction is one which, when it progresses, absorbs heat, right? And an example of this, again, if you have a small test tube with water in it, and if you had a few grams of, you can use sodium nitrate or potassium nitrate, what will happen is that when you feel the outside of the test tube, it's going to feel cool or cold, right? And that's because the dissolution of sodium nitrate or potassium nitrate is an endothermic process where it absorbs heat, right? So that's what happens in the case of an endothermic reaction. So in an isolated system, there'll be a decrease in temperature. And what will happen is that as far as the reaction is concerned, the energy of the products would be greater than the energy of the reactants because there's an absorption of heat, and therefore the reactants will absorb energy to form the products, which will be of a higher energy. Okay, so this is a pictorial representation of what happens in the case of an exothermic reaction. And if you understand this, then you should be able to appreciate what will happen in an endothermic reaction. So we have three situations here. This one is purely hypothetical, which is not grounded in reality. This would just simply won't happen, but it's a hypothetical situation which allows us to understand what's happening. In that all the heat that is generated from this exothermic reaction is released through the walls of the container, right? So in this case here, if the reaction is going on and it's exothermic, all the heat generated will be will escape into the rest of the surroundings, and therefore the temperature here will not increase. Now the surroundings are 25 degrees Celsius, so therefore the temperature here in this particular case will be the same as the surrounding because the heat is just basically lost to the environment. Now this is more likely to occur, the second setup here, right? Now in this case here, when the reaction is taking place, some of the heat will be lost to the environment, but the rest will be absorbed by whatever the contents remaining in the beaker, right? So therefore, as a result of that, the temperature will increase, right? From 25 to, let's say, 32.2 degrees Celsius, right? Now, if you have an isolated system, which is what we have here, this is basically two styrofoam cups. Styrofoam is a material that does not allow energy or heat to pass through it, right? And it's closed off because you have a stopper here, and you have a hole, but you have a thermometer here stuck in it. And the purpose of the thermometer, of course, is to measure the temperature increase that is taking place as the reaction is going on inside here in the system. So basically, in this particular case, no heat will be allowed to escape from this reaction. So therefore, the temperature, the maximum temperature achieved here would be higher compared to what we had here. And as you can see here, the temperature in that case is 35.4 degrees Celsius. All right, so that's basically what happens in the case of an exothermic reaction. And as I said before, if you appreciate this, then you should be able to explain what happens in an endothermic reaction in each case. Okay, so let me move on now to talking about the internal energy change where the volume is remaining constant. Now, going back to this equation here, delta U is equal to Q plus W, right? Remember, internal energy is equal to the heat change plus the work that is done on the system, right? Now, in the case where the reaction is being carried out under constant volume conditions, that means that the volume does not change, which means that delta V is equal to 0. And remember, delta W is equal to minus P delta V. So if delta V is equal to 0, that means that W is equal to 0. And if W is equal to 0, that means that the change in internal energy would simply be equal to Q. All right? So it's also expressed as QV here. This little v just means that the volume is held constant. All right? So basically, under constant volume conditions, if you make sure that the volume doesn't change, then the internal energy change is all due to the heat change that is occurring in the reaction. All right? Now, in practice, that is pretty much not the case, right? It's very hard, if not impossible, in some cases, to keep the volume fixed. All right. In most cases, what will happen is that you can keep the pressure constant, which is basically what happens in the vast majority of reactions, right? So where you have a situation where the pressure is constant, then basically the internal energy would be equal to the heat change minus P delta V, because remember again, W, the work done, would be equal to minus P delta V, right? So basically they put minus P delta V in the equation where W is, and you end up with this equation right here. And we can rearrange this equation to get delta U is equal to, I'm sorry, QP is equal to delta U plus P delta V, right? So this is what happens in this particular case. In most cases when you do a chemical reaction, it's done under constant pressure conditions, and therefore this equation describes the energy changes that will take place under those circumstances, right? So the way we can interpret this qualitatively is that most of the thermal energy is released as heat, right? But there's some work that is done to expand the system against the surroundings to push back the atmosphere, all right? So that's basically what happens in the vast majority of reactions. Okay, and that's what we'll be talking about pretty much for the rest of this chapter when it comes to the energy change that occurs for chemical reactions. Basically, QP here represents that energy change for those reactions. Okay, so let's talk about another term that you're going to meet. Let me just see something here. Okay, so this term is enthalpy, right? And enthalpy, by definition, is the sum of the internal energy plus the pressure volume product of a system. In other words, enthalpy represented by the letter H is equal to U, which is the internal energy, plus the pressure times the volume, all right? So that's how you calculate the absolute enthalpy of a substance, right? Now, for a constant pressure situation, the equation we were introduced to was this: QP is equal to delta U plus P delta V, right? So it turns out that QP is the same thing as a change in the enthalpy of a reaction. So basically, the change in enthalpy of the reaction is basically the heat change of the reaction, all right? And an example is shown here: the reaction between magnesium and acid, hydrochloric acid, to form magnesium chloride and hydrogen. And hydrogen is a gas which will expand against the atmosphere, right? So as stated here, most reactions occur under constant pressure. So therefore, for most reactions, the heat change equals to the enthalpy change, all right? And that is basically one example. And like I said before, the vast majority of reactions are operating under constant pressure conditions, all right? So from here, we're going to discuss more about enthalpy. Let's talk about the properties of enthalpy. The first of which is that enthalpy is an extensive property. What does that mean? That means that it's dependent on the quantity of the substances involved in the reaction. So if you have a reaction where you have a certain amount of, let's say, one particular reactant, and the enthalpy is of a certain value, if you double that the amount of that same reactant, then the enthalpy value will be doubled as well. So as stated here, 2 logs on a fire gives off twice as much heat as 1 log, as a kind of analogy, so that you understand that the amount of enthalpy change occurring is dependent on the amount of materials involved. Now, because internal energy, pressure, and volume are all state functions, that means that the enthalpy is also a state function, which basically means that its value is dependent on the state, right? Temperature, pressure, all those things that I mentioned before, all right? And enthalpy changes have unique values. So delta H, as we said before, is equal to QP. And we're going to talk about later on how do we calculate these enthalpy values based on this fact. Okay, we can represent energy changes in a reaction using what are known as enthalpy diagrams. Now, these values, the delta H values, can be determined experimentally, all right? In most cases. And couple of things you need to keep in mind. Negative values indicate that the reaction is exothermic. We talked about that before, right? If delta H is negative, then the reaction is exothermic. And if delta H is positive, then the reaction is endothermic, all right? So in the case of an exothermic reaction, what you'll find is that as you go from the reactants to the products, there's a decrease in enthalpy, right? and therefore the enthalpy of the products will be less than the enthalpy of the reactants. And let me just say here, and I probably should have mentioned this before, the actual value, the absolute value of delta H will be equal to the sum of the enthalpy of the products. I should put this sigma sign here to represent sum, minus the sum of the enthalpy of the reactants. And this is a simplified way of expressing it. It's actually slightly more complicated because you have to take into account the stoichiometry of the reaction, which we're going to talk about later on. But generally speaking, it's the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. So if the enthalpy of the products is lower than that of the reactants, then delta H will be negative, which means that the reaction is exothermic, right? On the other hand, in the case of an endothermic reaction, the enthalpy of the products would be greater than the enthalpy of the reactants, right? And therefore, based on that same definition I just gave you, the difference in enthalpy would be positive in that case, right? And that means that the reaction would be endothermic, all right? Okay. All right. So let's talk about what happens when a reaction reverses. How does that affect the enthalpy value? Well, basically, if you reverse a reaction, the sign of delta H will be changed. Everything else being the same. If you don't change anything else, right? The only thing you're doing is reverse a reaction. That means that the sign of delta H is going to be changed. So therefore, if you're going in one direction for the reaction, if delta H is negative or exothermic, that means that going in the other direction, delta H will be positive or the reaction will be endothermic, all right? That's another thing that you need to keep in mind when it comes to doing certain calculations. So therefore, a cyclic process has a value of delta H equals 0. In other words, if you're going from A to B, which is positive, and going back from B to A, then the net result would be no change, right? Delta H would be equal to 0, all right? So here's an example of this. A natural chemical reaction example. Mercury 2 oxide, right? In order for it to be converted to the products mercury and oxygen, according to this equation, the enthalpy change for that would be plus 90.83 kilojoules, right? Going in the other direction is going to be the same magnitude, but the sign will be changed, minus 90.83, right? So basically, that's the change that reversing a reaction will have on the sign, all right? And that will become important when it comes to doing certain calculations. What else? Oh, okay, so let's look at these examples. The first one says, given the equation, and it gives you this equation, calculate delta H for the reaction, and it gives you this equation. So my question to you is this. I want you to compare this equation to this equation and tell me what are the two differences. There are two differences between those two equations. What's the first one? There are two differences between the first equation given and the second equation given.
Between like the hydrogen gas and
Okay, so if I'm getting what you're saying, you're talking about the coefficients.
yes.
Right, exactly. The coefficients are different. What's the difference in the coefficients?
Second one.
Exactly. Right. So the coefficient of each of these are reduced to a half in each of these, right? Okay, that's one difference. What's the other difference? What's the other difference between the two equations?
They're opposite of each other.
Right, you flip one to get the other, right? So the products of the first reaction would be the reactants of the second reaction and vice versa. Okay, so now the question is, how does those two differences, how does those two changes affect the original value of delta H here, which is given right here, right? So as she correctly said, all right, each of these has been reduced by a half, right? So basically, if you're going to reduce each of these by a half, so let's give you half H2 gas plus half I2 solid to give you HI gas, right? HI gas, right? That corresponds to a value of delta H, which is half of this, right? So the delta H value for this reaction that I just wrote would be half of 52.96 kilojoules, right? And then now to get from here to here, we have to flip the equation. So the reactants become the products, the product becomes the reactant. So how does that affect the sign of this? Delta H of this will be equal to what? Minus half of 52.96 kilojoules, right? So that works out to be equal to what? Minus half of 52 is, I'm sorry? 26.48 kilojoules. And that's it. And that's how you do that, right? Okay, the next question. Well, any questions for the first one? Any questions? Any questions? Okay, the next question says the complete combustion of liquid octane, and it gives you the formula, produce gaseous carbon dioxide and liquid water at 25 degrees Celsius, and at a constant pressure gives off 47.9 kilojoules of heat per gram of octane. Write a chemical equation to represent this information. Okay, so to be perfectly honest, the question is a bit unclear. What they're asking for, to be more clear, is this right here. Something like this. They want you to write down an equation where not only do you have the equation, but you have the correct delta H value associated with it, right? So I'm going to need some space for this. So let me just copy and paste this onto Word document. Okay, come on. Okay, so this is the question. So the first thing you have to do is write down a balance equation based on the information provided. Okay, so based on information provided, what would be the reactants, first thing? Mm-hmm. Well, no, reactants I'm asking for first, not products. So what would be the reactants? There are two reactants.
C8H10 and then
C8H18
H18 and then oxygen.
and then oxygen. And then what will be the products?
Carbon dioxide
Mhm.
and water.
Okay, very good. So now we need to balance this. So to balance this, what do we need to do? 8 in front of the CO2, 9 in front of the water. Well,
Multiply C8 and H18 by 2 first,
Yeah.
like that would work.
well, yeah, you could do that. What I like to do is do this. And then multiply everything by 2. So you're going to get 2 C8 H18 plus 25O2 to give 16 CO2 plus 18 H2O. Oops, 18 H2O. All right. So this would be the balance equation, right? Now the question says that under constant pressure, the reaction, and please note the wording here, the reaction gives off 47.9 kilojoules of heat per gram of octane. All right. So what that tells me is that we can express this information here as this, minus 47.9 kilojoules, right? And why do I say minus? Because it gives off heat, right? So minus 47.9 kilojoules of heat for every 1 gram of C8H18, right? Now, in this case here, what I need to determine delta H of here, based on this information, is what would happen if it were 2 moles. of octane, right? So what I will do first is I would multiply this by the molar mass of octane. So in other words, 1 mole of octane down here, and the molar mass up here. So basically, that would be 8 times 12.01, whoops, 8 times 12.01, plus 1/8 times 1.008. So according to my calculation, the molar mass of octane is 114.22 grams of C8H18, right? So that this will cancel out with that. And then the next step would be that I'll multiply by 2 moles of octane based on the equation right here, C8H18. And that value would be equal to the delta H, which is what we need to find. So let me do that calculation. So 47.9 minus times 114.22 times 2. And according to my calculation, rounded out to 3 sig figs, I got delta H being equal to minus 1.09 times 10 to the 4 kilojoules. So that would be the value here, minus 1.09 times 10 to the 4 kilojoules. All right. And that's basically how that is done. All right. Okay, any question about this one? Any questions? Any questions? Any questions out there in Zoom? Only one person is out there in Zoom, that's Addison Sneller. Okay, let me get back to the PowerPoint and move on to the next slide. Okay, now we're going to get into how do we deal with delta H and the stoichiometry, right? How does the stoichiometry affect the value of delta H? So basically, we can look at heat evolved as being a product and heat absorbed as being a reactant for the purposes of doing these types of calculations. And based on that, we can generate conversion factors involving delta H. So here's an example. Let's say we have the reaction between hydrogen and chlorine to form 2 HCl, and delta H for that reaction is equal to minus 184.6 kilojoules, right? So therefore, we can write down some relationships between different substances and the value here. So for example, the relationship between the hydrogen and the delta H value can be written like this, right? We can also write this in the case of the relationship between delta H and chlorine. And we can write this as far as relationship between delta H and HCl is concerned, right? So basically, you can use these conversion factors to do certain calculations, right? Depending on what your being has. In fact, I think the next, yes, there is actually an example based on that. This question is asking, what is the enthalpy change associated with the formation of 5.67 moles of HCl in this reaction? And it gives you the equation and the delta H value. So basically, the way I would do this is that I would start out with the 5.67 moles of HCl, and I would multiply this by a conversion factor, which relates the enthalpy change to the moles of HCl, and that would be 2 moles of HCl down below as the denominator, and minus 184.6 kilojoules above as the numerator. And then we do the number crunching. So 5.67 times 184.6 minus, and then divided by 2. So according to my calculations, running off the 3 sig figs, the answer is going to be equal to minus 523 kilojoules. And that's how you do that. All right. Okay, any questions about this one? This one is relatively simple. All right. Okay, so let's talk about calorimetry. This is basically a technique that is used to determine heat flow, right? And an instrument is used called the calorimeter, which is basically the device used to make this type of measurement, right? So you have different types of calorimeters with varying levels of sophistication. And the one that you see here on the screen is the ultimate in low technology. Basically, it consists of two styrofoam cups, right? We saw this earlier. Two styrofoam cups, one nested in the other, covered with a cork material, and you have two holes punched into the cork, one for the thermometer and the other one for a stirrer, right? And that's basically the setup, all right? So basically, we can use this to measure the heat change if you have a reaction taking place inside the cup. So let's say the reaction is exothermic, right? It generates heat. So basically what you do is record the change in temperature using the thermometer, and then based on the amounts of materials that you use to cause the reaction, you can determine the amount of heat change occurring for that reaction, right? Now there's a special type of calorimeter which is a bit more sophisticated, known as a Baum calorimeter. And this is used mainly for determining the enthalpy change occurring in the case of the combustion of organic compounds, right? Things have to be a bit more different compared to the simple one that we have over there. And basically, as you can see, this consists of what they call a steel bomb, which is basically a metal encased object where the walls are very sturdy. And basically, you have your organic material here, and then you have two wires that are led into it, which is connected to an external circuit. And the purpose of that is to deliver heat to the organic compound. And therefore, what will happen is that this will start burning, produces heat. The heat will pass through the walls of the Baum calorimeter into the water right here. And therefore, the change in temperature of the water will give you, will help you to determine the amount of heat that is produced. And there's a little stirring device right here, which is used to basically stir the water to make sure that the heat is evenly distributed in the water. And that's basically how this works. All right. Okay. Some other terms I need to talk about here, some of which you may have met before, right? Now, when it comes to calorimetry, the heat involved in a reaction is absorbed by the calorimeter and its content. So therefore, there's a relationship between the heat produced by the reaction and the heat that is absorbed by the calorimeter. And that is given by, I thought I had the equation here, hold on. Okay, let me write the equation down. So that is given by the simple equation, Q of the calorimeter is equal to minus Q of the reaction, all right? So the reason why we have the minus sign there is because if heat is generated by the reaction, then that means that that heat change will be negative from the reaction standpoint, but from the calorimeter standpoint, heat is being absorbed, right? So therefore, that's why we have a negative sign here, right? In a calorimeter, we measure the temperature change of water or a solution to determine the heat absorbed or evolved by the reaction, which is what I mentioned before. So we can have what is known as the heat capacity of a system, which includes, you can have the heat capacity of a calorimeter. And that is given by this equation right here. It is the amount of heat change required to change the temperature of the system by 1 degree Celsius or 1 Kelvin. And it is given by this equation right here. C, and by the way, this is uppercase C, is equal to Q, which is the heat change, divided by the change in temperature, right? And let me just say here that the change in temperature, delta T, is T final, I'm going to say T2, minus T initial, which is T1, right? And this is true for any change in anything that you're measuring, right? We saw that in the case of enthalpy change. That is also true in the case of temperature change. It's a final value minus the initial value. It's always final minus initial, all right? So in the case of the change in temperature, it's a final temperature minus the initial temperature, right? And basically, this is how you calculate the heat capacity. And then there's a molar heat capacity, which, to be perfectly honest, I don't anticipate us dealing with. That's the heat capacity of 1 mole of a substance. Now, the next term, you definitely will be working with this, is called the specific heat. And that is the heat capacity of 1 gram of a pure substance, right? And that modifies this equation a bit, right? So basically, the specific heat, which by the way is represented by lowercase c, is equal to the heat capacity, which is represented by uppercase C, divided by the mass of the substance. Another way of stating it is Q divided by M times delta T, or you can rearrange it to get Q is equal to C times M times delta T, right? Now, Q is the heat change, C is the specific heat, M is the mass, and delta T is the change in temperature. Again, it's final minus initial. And let me just say that delta T can be expressed in either Kelvin or Celsius. It doesn't matter. It's not going to affect in any way the rest of the calculations. All right. Let me just say also that C is a physical quantity that can be used to help to identify what a substance is, right? So it's basically something similar in terms of its importance to density, for example, or melting point or boiling point. It's one of those things that you can use to help you to identify what a particular substance is, right? So let me see here. Okay. I'm going to say more on that later on. Let's look at this example. So this question says, calculate the heat capacity of an aluminum block that must absorb 629 joules of heat from its surroundings in order for its temperature to rise from 22 degrees to 145 degrees Celsius, right? So remember now we said that that uppercase C, which is the heat capacity, is equal to Q divided by delta T, right? So in this case here, C is equal to Q, which is 629 joules, divided by delta T, which would be the final temperature, 145 degrees Celsius, minus the initial temperature, which is 22 degrees Celsius. All right? So let's see what that gives. 145 minus 22. So according to my calculation, this would be equal to 629 joules divided by 123 degrees Celsius. So 629 divided by 123. And according to my calculation, the final answer will be 5.11 joules per degree Celsius. And that's how you do that. Okay, any questions about this one? Any questions? All right, next. So more specific heat, right? So this is the relationship right here. This is the equation. Q is equal to mass times the specific heat times the change in temperature, right? So basically, again, we have to pay attention to the signs, right? What the signs actually mean, right? So if delta T is positive, that means that there's a change in temperature, which corresponds to an increase, right? If that's the case, then Q would be positive as well, which means that the system is absorbing heat, all right? The mass cannot be negative and the specific heat cannot be negative, right? So the only thing that can be negative or positive would be delta T. And as I said before, if this is positive, that means Q is positive, which means that the system is gaining heat. On the other hand, if delta T is negative, that means Q is negative, which means that the system is losing heat, right? Now, there is another unit of heat, which is known as the calorie unit, which is still used to some extent in engineering, physics, and so on. And the relationship between the calorie unit is what you see right here. 1 calorie is equal to 4.184 joules. And this is based on the properties of water. Basically, what was decided was that the calorie represents the amount of energy change required to change the temperature of 1 gram of water by 1 degree Celsius. All right. And then there's another unit known as the full calorie, which is the units of which is CAL, uppercase C, or kilocalorie, which is equal to 1,000 of the calorie that we mentioned here before. All right. So those are just some other units of energy. Okay, so this was the table I was thinking of, which gives you basically a small sample of different substances and their respective specific heat. And what you'll notice is that metals tend to have very low specific heats, liquids tend to have higher specific heat, and water has an unusually high value here compared to the others. And that is due to a phenomenon known as hydrogen bonding, which hopefully we will get to later on. All right. So as stated here, most metals have low values of specific heat, and water has a higher specific heat than almost any other substance. Okay, so let's look at a couple of these examples. This question says, how much heat in kilojoules and joules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100 degrees Celsius? I think I can fit this up here. So the equation, of course, is Q is equal to M times C times delta T, right? So Q will be equal to the mass of the water, which is 225 grams, times the specific heat of water, which would have to be provided to you, right? So that is equal to 4.18 joules per gram degree Celsius, multiplied by the change in temperature, which is 100.0 degrees Celsius minus 25.0 degrees Celsius. And that's the change in temperature, right? And if you work out equal to 75.0 degrees Celsius, and then we go ahead and do the rest. So 75 times 4.18 times 225, and round this off to 3 sig figs. So according to my calculation, this works out to equal to 7.05 times 10 to the 4 joules. All right. So that's basically how that is done. Pretty straightforward application of the equation. Okay, now this question says, what will be the final temperature if a 5.00 gram silver ring at 37.0 degrees Celsius gives off 25.0 joules of heat to its surrounding? And it says use the specific heat of silver listed in table 6.1. So let me go back to that table and look up. Okay, silver, 0.235. So the specific heat of silver is 0.235 joules per gram degree Celsius. Okay, so the question is asking for the final temperature, right? Now, since Q is equal to this right here, what I would do first is try to find out what delta T is. So delta T, based on that equation, would be equal to Q divided by M times C. So Q is 25.0 joules. M is 5.00 grams times C, which is 0.235 joules per gram degree Celsius, right? So that's delta T. So let's see what delta T is equal to. 25 divided by 5 times 0.235, and according to my calculation, delta T, oh, that can't be right, let me see. 25 divided by 5 times 0.235, so 21.2, okay, I guess I was right the first time. 21.2 degrees Celsius. So that would be the change in temperature. But the question is not asking for the change in temperature. What the question is asking for? The final temperature, right? So remember we said that the final temperature, or I should say, sorry, the change in temperature is equal to the final temperature minus the initial temperature, right? So I'm going to write down here, delta T is equal to T2 minus T1, right? So therefore, to find the final temperature, T2, that will be equal to delta T plus T1, right? So delta T is 21.2 degrees Celsius plus T1. What's the initial temperature? 37.0 degrees Celsius, right? So 21.2 plus 37, according to my calculation, works out to be 58. Let me do this again. 21.2 plus 5 plus 37.0, 58.1. 58.1 degrees Celsius. And that's how you do that. All right? Any questions about this? Any questions? Any questions? Okay. Here's another example. Now, in this case, this one is interesting because it says here, you have a sample of metal, it gives you the mass, 15.5 grams. It is heated to 98.9 degrees Celsius. And then you drop it into water, and it gives you the mass of the water. And it says that the temperature of the water rises from 22.5 degrees Celsius to 25.7 degrees Celsius. And the question is asking for you to calculate the specific heat of the metal alloy. All right, so let's think about what's happening here. You have a metal which is at this temperature right here, relatively high. The water, which is what, 98.9 degrees Celsius, right? The water is cooler initially at 22.5 degrees Celsius. when you put the hot metal in the cool water, what's going to happen? You're going to have heat transfer from the hotter metal to the cooler water, right? So what's going to happen? The temperature of the metal will fall and the temperature of the water will rise until you get to a state of thermal equilibrium, right? Where the temperature of the metal and the temperature of the water is the same, right? So therefore, the amount of heat that is lost by the metal will be equal to the amount of heat that is gained by the water until you get to that particular equilibrium position, all right? So basically, the first thing I'm going to do is, in order to solve this problem, is that I'm going to start off with writing down this equation. The heat change for the water will be equal to the heat change of the metal, right? And in fact, I need to put a minus sign here because the heat change of the water would be negative compared to the heat change of the metal because the metal is losing heat while the water is gaining heat, right? Now remember, for each of these terms, we can write down an equation looking like this, right? Q is equal to M times C times delta T. So for Q water, I'm going to write down MW times CW times change in temperature W is equal to minus M of the metal, mass of the metal, times the specific heat of the metal times the change in temperature of the metal. All right. Now, what the question is asking for is the specific heat of the metal, right? So basically, to isolate this by itself, of course, we know by algebra, we divide both sides in this case by minus mm times delta T minus mm times delta T, right? So this will cancel out with that, the negative signs will cancel, and you're going to end up with delta Tm canceling out here and here. So this will be equal to the specific heat of the metal, all right? So the next thing I'm going to do is put the numbers in. This should be delta Tm here, right? So the next thing I'm going to do is put the numbers in. I'm going to plug the numbers in. Now here you have to be careful, right? Because you have to interpret what the question, or I should say, you have to interpret the information that is given in the question in order to put the numbers in the right place, right? So the question says that the mass of the metal alloy is, well, let's start off with the mass of the water. That's 25 grams. So I'm going to put 25.0 grams here times the specific heat of water, which again should be given to you, which is 4.18 joules per gram degrees Celsius times the change in temperature of the water. Now, this is where you have to be careful. The question says that the temperature of the water rises from 22.5 to 25.7. So that means that the change in temperature will be the final temperature, 25.7 degrees Celsius, minus the initial temperature, which is 22.5 degrees Celsius. All right? And then now below here, we're going to have minus the mass of the metal, which is the 15.5. 15.5 grams times the change in temperature of the metal. Now, what's the change in temperature of the metal? Well, the final change, or I should say the final temperature of the metal will be the final temperature of the water, right? Because remember, we're talking about thermal equilibrium. So here I'm going to put, in parentheses, 25.7 degrees Celsius minus the initial temperature of the metal alloy, which is 98.9 degrees Celsius. All right, and then we do the calculation. So what I'm going to do is work out what's within the parentheses, 25.7 minus 22.5. And for this part, I got 3.2 degrees Celsius, and then 25.7 minus 98.9. So this part, I'm going to put here, minus 73.2 degrees Celsius, all right? And then we do the rest of the calculation. So that would be 25 times 4.18 times 3.2. And then I'm going to divide that by 15.5 negative times 73.2 negative. And according to my calculation, now this I'd have to round up to 2 sig figs because of the 3.2. So the answer I got here is 0.29, and the units here will be joules per gram degrees Celsius, because degrees Celsius will cancel out here and here. The grams will cancel out here and here. So you're left with this right here. And that's how that is done. All right? Any questions about this one? Any questions? Okay. So what I'm going to do here is get you started on assignment number 6. And this is for you. And for Addison, I haven't forgotten you. I'm going to publish this assignment in Canvas. So let me go here, here, here. And let me go here. Okay, so assignment 6. Oh, and by the way, hold on. Okay. Oh, okay, so so I've included this addendum here. So what I'm going to do is I'm going to publish this here, which is assignment 6, and then there's an extra page. I'm going to publish that as well, which I've already included in your handout that I've handed out here. But for Addison, make sure that you download not only this one right here, but this one right here. All right. So what I'm going to do is open this up. And we're going to start with the first question, which is calculate the total change in energy. Now they use the symbol delta E. We use delta U. It's the same thing. All right. So the question is asking for you to calculate the total change in energy, internal energy of a system when 400 joules of heat is applied to expanding oxygen and the gas does 35 joules, 350 joules of work, right? So if you remember, I said you have to pay attention to how the question is worded in order to apply the appropriate signs for the different terms. So the equation, of course, is delta U is equal to Q plus W, right? So in this particular question, delta U is equal to Q. So what is Q in this case based on the information provided? 400 joules. And not only that would be positive 400 joules because it's the amount of heat that is applied, right? Okay. And then what about oh, hold on. Did I say Q or W? In any case, this is Q, right? And then what is W? Notice the wording. It does 350 joules of work. I'm sorry? It will be 350 joules, but what will be the sign? That's the important thing. Negative, exactly. Minus 350 joules. So remember, you have to pay attention to how it's worded. So the answer here would be 50 joules, would be delta U. All right? Okay, any questions about this one? Any questions? Any questions? All right. Number 2 says, calculate the kinetic energy in joules, calories, and kilojoules of a particle, and it gives you the mass, and it gives you the velocity, all right? So let me clear this. and scroll down. All right. So just to remind you, the formula for kinetic energy is equal to half mv squared, right? Where m is the mass in kilograms and the velocity will be meters per second, so that means that will be squared, right? So if the mass is in kilograms and the velocity is in meters per second, that means that the kinetic energy units would be in joules, right? Okay, so in this case, you're asked to calculate the kinetic energy of a particle and it gives the mass and the velocity. So in this case, kinetic energy will be equal to half times the mass. Now notice, the mass is in grams, right? So I'm going to write down half of 9.11 times 10 to the minus 28 grams. So what that means is that we have to convert this to kilogram by multiplying by 1 kilogram over 1,000 grams. And then we multiply that by the velocity squared, which is 6.00 times 10 to the 5 meters per second, and all of that would be squared. All right. So let's see what that gives. 6 times 10 to the 5 squared divided by 1,000 times 9.11 times 10 to the minus 28 times 0.5. And according to my calculations, and please correct me if I'm wrong, but I got 1.64 times 10 to the minus 19 joules. All right. Any questions about this? Okay, so that's the first part. The second part is asking for you to calculate the same value in calories. So I'm going to take the 1.64 times 10 to the minus 19 joules, and I'm going to multiply by 1 calorie over 4.18 joules. So 1.64 times 10 to the minus 19 divided by 4.18, and according to my calculation, this works out to be equal to 3.92 times 10 to the minus 20, and the units here would be calories. All right. Okay, any questions about that one? Okay, the final part is asking for you to do a conversion from joules to kilojoules. Let me just put that in this box right here. So in this case, it's 1.64 times 10 to the minus 19 joules multiplied by, so above I'm going to put 1 kilojoules, and below I'm going to put 1,000 joules. So 1.64 times 10 to the minus 19 divided by 1,000. And according to my calculation, that is equal to 1.64 times 10 to the minus 22 kilojoules. And that's how that is done. All right. Any questions about any of these? Any questions? Okay, in the case of number 3, it says a 1.0 gram sample of propane is burned in a calorimeter. The temperature rose from 28.5 degrees Celsius to 32.0 degrees Celsius. And it says that the heat of combustion is 10.5 kilojoules per gram. Calculate the heat capacity of the calorimeter apparatus in kilojoules per degree Celsius, right? Now, to remind you, the equation for the heat capacity is this: C is equal to Q over delta T. So in order for us to calculate the heat capacity, we need 2 things. We need the amount of heat change as far as the calorimeter is concerned, and we need also the temperature change, all right? Now, we don't have, well, firstly, delta T is easy to calculate because delta T would be the final temperature minus the initial temperature, which is 28.5 degrees Celsius. All right. So let's do that calculation first. So 32 minus 28.5. So according to my calculations, this is equal to 3.5 degrees Celsius, all right? Okay, now what we need to calculate in order to get C is find out what Q is, right? Now, in the case of Q, we're not given that directly, but what we're given is that the heat of combustion of propane is 10.5 kilojoules for every gram of propane, right? Now they gave us a 1 gram sample, so therefore Q in this case would be equal to 1.0 grams multiplied by 10.5 kilojoules per gram, all right? And technically speaking, the heat of combustion will be negative because combustion involves an exothermic reaction. So this will be equal to basically minus 11 kilojoules. So this will be Q of the reaction, right? Now Q of the reaction will be equal to minus Q of the calorimeter, right? And this is what we are using to determine C. So therefore C will be equal to 11 kilojoules divided by the change in temperature, which is 3.5 degrees Celsius. So let's see what that gives. 11 divided by 3.5. So according to my calculation, this works out to be 3.1 kilojoules per degrees Celsius. And that would be the answer. All right. Okay. Any questions about this one? Any questions? All right, let's clear this and scroll down. Okay, so this one is kind of similar to the example that we saw before. Let's just see something. Okay. So this one says when 72 grams of a metal at 97 degrees is added to 100 grams, and I just realized there's a typo here. So make sure you make this change. There should be a decimal point right here, right? So make sure you make a note of that, all right? Okay, so the question says when 72 grams of a metal at 97.0 degrees is added to 100 grams of water at 25.0 degrees, the final temperature is 45.5 degrees Celsius. What is the heat capacity per gram of the metal? The heat capacity per gram is basically the same thing as the specific heat of the metal, right? So we did one example which is very similar to what we have right here, right? So let me ask you, what would be the first step? And you feel free to go back in your notes to see what we did in that example. What would be the very first step in this process that you would take in this process? What would be the first step? Let me help you out. Q metal is equal to minus QW. Remember that? Okay. What's the next step?
The equations with the mass, the specific heat and the delta heat. I would say we should put the water in.
Is equal to minus MW times specific heat of water times delta TW. And then what?
Just want to divide by the mass, and it's change temperature, so you have a specific heat on one side.
I'm sorry. So this would be the mass of the metal times the change in temperature of the metal. Okay. So this will cancel with that, this will cancel with that, so you're left with this being equal to Cm. All right, so what next?
Probably want to find the change in temperatures.
I'm sorry?
Find the changes in temperature for like drilling.
Okay, let's do that for the water. What's the change? Well, let's find the mass of the water first. What's the mass of the water? 100 grams times the specific heat of water, which is given as 4.184 joules per gram degree Celsius. And then, as you suggested, find the change in temperature of water, which is what? 45.5 degrees Celsius minus 25.0 degrees Celsius. Okay, and then we divide that by the mass of the metal, which is what?
72 grams.
72 grams times the change in temperature of the metal. So what's the change in temperature of the metal? Based on the information provided.
45.5 Celsius.
45.5 degrees Celsius minus
97.
97.0 degrees Celsius. Okay, very good. So the top part, I'm going to do the 45.5 minus 25, and that gives 20.5 degrees Celsius. And then from down here, it's 45.5 minus 97, and that gives minus 51.5 degrees Celsius. And then we do the rest, so that's 100 times 4.184 times 20.5, and then we divide that by 72 times 51.5, and according to my calculation here, oh, is that right? Let me redo this again. I think I made a mistake. 100 times 4.184 times 20.5 divided by 72 times 51.5. Ooh, okay. So the answer I got is how many sig figs? 2 sig figs. So 2.3, and the units would be again joules per gram degrees Celsius. And that's how you do that. All right. Any question about this one? All right. Okay, so if you understood how to do this one, I'm going to leave question number 5. Let me clear this first. I'm going to leave number 5 for you to do. Let's jump to question number 6. It says a sample of cobalt A with a mass of 5.00 grams is initially at 25 degrees, and when this sample gains 6.70 joules of heat, the temperature rises to 27.9 degrees Celsius. Another sample of cobalt B with a mass of 7.00 grams is initially at 25.0 degrees Celsius. If sample B gains 5.00 joules of heat, what is the final temperature of sample B? All right, now the key thing in this question is that both sample B and sample A are the same substance, right? So that means that they would have the same value for the specific heat. So based on the information provided in the case of sample A, you're given the mass, you're given the initial temperature, you're given the amount of heat, and it says it gains this much heat, and it says that the temperature rises to 27.9. So we can use this equation to find the specific heat of the cobalt. So C, which is the specific heat, would be Q divided by M times delta T. So Q is 6.70 joules divided by the mass, which is 5.00 grams, times delta T, which is 27.9 degrees Celsius, minus 25 0.0 degrees Celsius. And let's see what that gives. 27.9, I'm going to work out this part here first, right? 27.9 minus 35. So I got 2.9 degrees Celsius here. And then we do the rest. So 6.7 divided by 5 times, hold on, 6.7 divided by 5 times 2.9. And the answer I got, rounded off to 2 sig figs, would be 0.46. And the units here would be joules per gram degrees Celsius. So that is the specific heat, right? Now, let's move on to the next part of the question. It says another sample of cobalt B has a mass of 7 grams, initially at 25 degrees, and it gains 5 joules of heat. What is the final temperature of the sample? So in this case, we need to find what delta T is, the change in temperature. That will be equal to Q over M times C. Now, in the case of the second sample, Q is 5.00 joules, M is 7.00 grams, and C is what we calculated before, 0.46 joules per gram degrees Celsius. So let's see what that gives. That gives 5 divided by 7 times 0.46. And according to my calculation, now in this case, I'd have to round off to 2 sig figs, which would be 1.6 degrees Celsius, right? Now remember, that is delta T, which is the same thing as T2 minus T1, right? What we're trying to find is T2. So T2 would be equal to delta T plus T1. Delta T is 1.6 degrees Celsius, and T1, the initial temperature, is 25.0 degrees Celsius. So you're going to add these two together, and this will give you 26.6 degrees Celsius as the final answer. All right, and that's how you do it. Okay, any questions about this one? Any questions? Okay. Let me see here. Let me scroll down to see what's next. Okay, now in the case, let me clear this first. In the case of question number 7, it gives you the balanced equation for the reaction, and it gives you the enthalpy change of the reaction. And it says that it's asking a couple of things actually. It's asking for the enthalpy change when 2.00 moles of methane are burned, right? So based on this equation here, for every 1 mole of methane, this is the enthalpy change, right? So therefore, what we can do is write down where we're going to start off with 2.00 moles. And we're going to multiply by a conversion factor, which represents the relationship that I just mentioned. Basically, you're going to have minus 890.4 kilojoules for every 1 mole of methane. So it's a simple calculation. This is 2 moles of methane here. So this will cancel out with that. So basically that would be 890.4 minus times 2. So this rounded off to 4 sig figs will give you minus 1781 kilojoules. And that's how that is done. All right. Okay, so if you understand A, how would you approach B? Because in the case of B, they did not give you the moles of methane, they gave you the mass in grams of methane, right? So let me hear your suggestions as to how you would tackle the B part. Yes, sir.
Would you convert the mass into moles?
Exactly. So we're going to start off with 22.4 grams of methane. And then we're going to convert that to moles, right? So 1 mole of methane will go above. And then the molar mass of methane would be 4 times 1.008 plus 12.01. So that will be 16.04. 16.04 grams of methane. All right. So that cancels with that. What next?
Bring 5 mass. Oh, wait, no.
We did that already. What's the next conversion factor?
The enthalpy.
Exactly, minus 890.4 kilojoules over 1 mole of methane. Right? So this will cancel out with that. So let's see what this gives. 22.4 divided by 16.44 times minus 890.4. And according to my calculation, now this would have to be rounded out to 3 sig figs. Actually, I'm sorry. For the first one, it should be 3 sig figs. So that should be a 0 here. So please make note of that. And the same is true for this one, which would be minus 1240 kilojoules. And that's how you do that one. All right. Any questions about this one? Any questions? Okay. Let me clear this. Okay, now in this case, it says if you're to attempt to make 45 grams of methane from CO2 and H2O, what is the enthalpy change in this case? Now, what you're talking about is the reverse of this reaction. So what happens to the sign when we reverse the reaction? It changes from negative to positive. So basically, you're going to do the same thing as you did in B, but the only difference is that you're going to use a positive value of the enthalpy change. So you're going to start off with 45.0 grams, 45.0 grams of the methane, convert to moles, so that would be 1 mole of methane over, what was it, 16.04 grams of methane, and then you multiply by the positive value, which was minus 890, well, positive 890.4. So this will be 890.4 kilojoules for every 1 mole of methane. And that's it. So 45 divided by 16 times 890.4. And according to, again, you have to round off to 3 sig figs, which according to my calculation, that would be equal to 2.50 times 10 to the 3 kilojoules. And that's how you do that. All right. Okay, any questions about this one? Any questions? All right, let me clear this here. By the way, what time is it? Ah, oh, okay. Having too much fun. Okay, let me see what question number 8 is all about. Okay, I will leave question number 8 for you to do. If you understood what we did in question number 7, you should be able to do question number 8. Oh, okay, you know what? I'm going to stop here for today because we haven't done Hess's law, which is what, question 9. Let me see, question 9, number 10, and 11. Okay, yeah, so we have to cover Hess's law first before we can do those questions. So I'm going to call it a day for today, all right? If I'm not mistaken, assignment number 5 is due today, right?
Yes.
Okay, good, all right. So make sure you complete that and submit it by midnight tonight. And I'll see you guys, well, I'll see you then. Alright,
I was wondering,
good man.
I sent you a message in Canvas, I think on like Sunday, so you might have just missed it, but I was curious if you'd be able to publish the PowerPoints maybe like for
Oh,
the following week, like maybe the Friday before something, just so it's,
oh, okay.
that way I can do the notes over the weekend.
Oh, okay. Yeah, I guess I could do that. We probably need to remind you because. So what did I not publish? Let me see it.
Cause I think so far I was five, I don't know if you've done six yet.
Let me see here. Okay, so this is. All right, 6. All right, tell you what. Before I forget, let me publish. 7.
Awesome. Thank you so much.
Yeah, no problem. Okay, and